This is Bradley Needham. I'm going to be talking about some of the mutating sequence operations. Now the C++11 standard lists 37 mutating sequence operations, so I won't be talking about all of them. I'm just going to cover a few of them, and hopefully that'll give you an idea of how to use any of them. So first let's go ahead and start with the copy operation and its variants. So I'm going to create a couple of collections here. I have my two collections. I want to go ahead and copy the collection 1 to collection 2. I can use the copy operation to do that, and I will pass the range, the first range, which is the source range, so collection 1 from the beginning to collection 1 to the end, and then I will pass the output range, or what it's going to be copied to, which is going to be collection 2 begin, starting collection 2 begin. You'll find this a lot in the STL, where you have an algorithm that has a source range, so you will have a begin and an end to it, and then an output which only has a begin. Algorithms work with iterators, right, and ranges, and they know nothing about the collections that are backing them. So whenever you see this, it's important to note that it is your responsibility to make sure that there are enough elements in collection 2 to support the copying of all the elements from collection 1. So collection 2 has to be at least as large as collection 1 in this case, and that's why in here you see that I've initialized collection 2 to be the size of collection 1, and therefore I know that there is enough space to hold all of the elements being copied. So let's go ahead and print these out, and I'll do the same thing for collection 2. Let's run that, and we get our two collections printed out, both with the same content. Well, remember, the algorithms work with ranges, so I do not have to pass the entire range of this collection. The algorithm doesn't know that that's a full collection or whether it's part of a collection. So I could, for example, start at the fifth element there and maybe end 4 elements back from the end. And notice my collection 2, the subrange, right, from the fifth element to the fifth element back here is what was copied into my secondary collection. And I have a bunch of zeros left in here, and that's because this collection was initially sized to the full size of the first collection, and it was initialized with default values for the integers that are put in there. Now after this copy, I probably don't actually want all of this extra space in here. So one thing I can actually do is I know that copy returns to me an iterator, and that iterator that copy returns to me happens to be the logical end iterator for the new values that have been copied into collection 2. So if collection 2 happens to be larger than the range that is being copied, it will tell you here is where the end is. After I finished copying everything to collection 2, here's where that end is. And I can use that to do something like erase the rest of the values in collection 2. Now when I run it, collection 2 only has the contents that is associated with the copy operation that was performed. So another thing to note about algorithms that I think we've seen before is that algorithms deal with iterators, right? We described the fact that this is dealing with just an iterator, and we know that there are things called iterator adapters, right? And iterator adapters allow us to convert some things that might not be iterators to actually look and behave like iterators. And an example of that is an OStream iterator. So I'm going to create an OStream iterator that is going to wrap the output stream, the standard output, and it allows for a delimiting character like this, where I'm going to say between each element that you output, I want you to add a space. And one of the things I can do with that, which is kind of neat, is that instead of having this for each loop here where I'm doing the printing, I can actually copy the contents of these containers to the standard output. And the way I do that is we'll just get rid of this for each now, and we'll change this to a copy. and I'm going to copy again the range collection 1 begin to collection 1 end. But what I'm going to copy it out to is my OStream iterator. Now again, I don't have to worry about here the size being, because an OStream iterator is just a stream, and so its size just keeps going, and I just keep printing things out to it. And I can do the same thing for collection 2 here, and here we get collection 1 using copy, collection 2 using copy. Another thing we can do is if we were printing the subset again, so let's go ahead and just use our subrange out of, let's run that again just so we can see that we're getting our subrange. Instead of having to go through the trouble of erasing this here, the other thing I could do is I could create a back inserter, and what a back inserter is going to do is a back inserter is going to actually create an iterator so that copy is happy with it being an iterator, but it's going to, every time you try to dereference the iterator, it will actually push back a value onto the vector. So it'll call pushback, which will then allocate new memory for the value that's being stored. So I don't need the erase anymore. You run it, we get the same values out. And notice I didn't have to use my iterator here because I wasn't doing the erase, and so I didn't need to know the end section because it was already an end section that was available. Okay, so there's a few other copy operations. One that comes now with C++11 that people have been asking for a while is copy if. And if basically means that the copy operation is going to take a predicate, and so instead of simply just doing the copy altogether, we might want to only copy to the new collection if the value happens to be odd. And we can create a predicate. We're going to get rid of this print function. We don't need this print function anymore. We can create a predicate, run that, and notice what we get passed into collection 2 is just the odd values that were in the original collection. If you don't have C++11, you can still have pretty much the same behavior as copyif with remove copyif. You just, of course, have to change the predicate, right? And in this case, I could simply change the predicate to is even. You could also create one that is not is odd. This should, of course, give us the same output, and it does. And of course, there is other ways to do this with function objects in the functional header file. So the copy algorithms, we get this starting range, which happens to be a source range, and then we have a begin iterator, which represents the output range. And the requirement again was we have to make sure that we do what? That we have enough values in this output range to support copying or transferring of all of these values that are in the input range. Another mutating algorithm that you might see are ones that just operate on the range passed to them directly. So that might be something like partition. And partition takes the range that you want to operate on and then the predicate, and what it's going to do is it's going to basically separate these so that the even numbers are on one side and the odd numbers are on the other. So example, if I run partition here, this is going to modify collection 1 directly through this algorithm. I run it, and you notice here that we have the even values first and then the odd values. If I took the iterator returned from partition is basically the iterator that specifies right where this partition occurs, right? Where are the odds and the evens in place? I can basically print out the first part of the partition and the last part of the partition. So if I'm going to do that, I'm going to go from begin of the collection to the iterator, and for this one I'm going to go from the iterator to the end. If I run that now, we can see the first is the even numbers and this last is the odd numbers, still within the same collection here. And of course, if I change this, it'll simply reverse the order of the partition and have the odd numbers first and then the even numbers in the partition. Alright, so that's an example of a mutating algorithm that mutates basically the actual collection that's passed in rather than having a secondary collection. Alright, so the other algorithm I'd like to go over, which is a common algorithm you'll see, is transform. Transform also takes in the starting range. That range is, we're going to do it from collection 1 begin to collection 1 end. And it takes an output, the starting iterator for an output. And then we're going to provide a function that's going to do the transformation. So in this case, we're going to go ahead and write ourselves a function called square. So now here in my call to transform, I simply pass the function square, and let's go ahead down here and make sure we print out. We're going to switch these back to printing out the entire collections, and let's run it. Alright, so notice what transform did was basically it took every element in collection 1, it invoked the function on that element, and took the result of that invocation and placed it into the collection 2. So we have, right, 2, 4, 3, 9, 6, 36, 5, 25, but you can see that it put in all of the squares of each of these values. Now, the interesting thing about transform, which is nice, is that you can do what's called an in-place modification. So these are mutating sequence operations, and in this case I'm doing the operation, but I'm transforming the values in collection 1. I'm not changing any values in collection 1, I'm simply putting the values into collection 2. The transformation is ending up in collection 2. But if I wanted to basically transform collection 1 itself, all I would have to do is actually pass the start iterator here for collection 1, and that would do an in-place transformation so that collection 1 was then actually transformed by this function again, or by this callable object. So here's collection 1 being transformed to the squares. The other version of transform takes two input ranges. So it takes the initial range, then it takes a secondary range. So this is actually the beginning of a secondary range. Again, we have to make sure that there are at least as many values in this range, the start where this range starts, as there are in the range that is described in the first two parameters here. And then it takes the output range and a function now that has to be a binary function. So again, this is a unary function because it only takes one parameter. So now to transform, we're going to pass that function, multiply, and this is going to take every element from collection 1, begin to end, and it's going to take each element from collection 2 here, and then it's going to apply the callable object multiply and put those results into collection 2. So let's go down here and make sure that we print out collection 2 again, run it. And sure enough, if we look at what we have 2 times 9, which is 18 for collection 2. We have 3 times 1, which is 3. We could also put this into a third collection if we wanted. So again, this is also an in-place modification, right? Because it's modifying collection 2 again, and that was part of the input. But if we had collection 3 here and we just used collection 3 as the output, and let's go ahead and print collection 3 as well. And then we run it, and we get what we're expecting. So collection 1 is 2, collection 2 is 9, and the result of calling multiply on that is 18. I hope that helps.